Back, and this one on the topic of climate and sustainability, where we will think about the atmosphere and also think about water. And it's going to be chaired by Deb Gracio from Pacific Northwest National Lab. Deb is an associate lab director for National Security, the National Security Directorate at PNNL. She oversees a portfolio of national security programs and partnerships. And under her leadership, PNNL delivers scientific insights, tools, methods, deploy impactful science and technology to sponsors in DOE, and the Department of Homeland Security, the Department of Defense, the intelligence community, and the National Nuclear Security Administration. Deb is going to introduce the members of the panel, and then each will speak with some introductory comments, and then we'll move to general discussion. So thank you very much, Deb, for agreeing to do this. It's over to you.
Thank you. Sorry about that. Good morning. My name is Deb Gracio, as Michael said, the Associate Laboratory Director for National Security at Pacific Northwest National Laboratory and a member of the Washington State Academy of Science. I'm honored to moderate this distinguished panel on an urgent and transformative topic, using AI to explore, discover, and understand climate and sustainability in Washington State. As many of you are aware, the Pacific Northwest and Washington State specifically face unique climate challenges. Our intricate interplay of mountains, coastlines, forests, and an urban area makes us both a microcosm of broader global climate issues and a unique test bed for innovative solutions. Changing precipitation patterns, rising temperatures, wildfires, and sea level rise are not distant threats, but realities that impact our communities, our economies, and our natural ecosystems. At the forefront of our scientific technological responses to these complex challenges is artificial intelligence. AI's capacity to analyze vast data sets, identify patterns, and generate predictive models holds immense promise for advancing our climate science and informing policy decisions. From enhancing weather forecasts to optimizing renewable energy deployment, AI-driven climate modeling is not just about prediction, it's also about actionable insights that can drive meaningful change. Today's panel brings together experts in the fields of climate sciences. Our panelists have been pioneering the integration of AI and climate science, and they are here to share their insights, experiences, and visions for the future. Our discussion will cover the potential of AI to revolutionize climate modeling, the specific challenges and opportunities it presents for both Washington State, and how we can bridge the gap between complex models and practical policy relevant outcomes. Whether you're a researcher or a policymaker, today's session aims to equip you with a deeper understanding of the current innovations in climate and modeling and foster a collaborative approach to tackle climate change with the aid of AI. Thanks for joining us. Without further ado, let's dive. For almost 35 years. Her research has focused on land-atmosphere interactions, climate extremes, land surface processes, and aerosol cloud interactions. As chief scientist of the Energy Exascale Earth Systems Model, or E3SM, supported by the Department of Energy, she leads a team of researchers in developing state-of-the-art capabilities for modeling human Earth system processes, leveraging DOE's next-generation high-performance computing capabilities. Dr. Leung is an elected member of the National Academy of Engineering, a fellow of the American Meteorological Society, the AAAS, and American Geophysical Union. She's been recognized with numerous awards throughout her career, including the most prestigious 2021, the DOE Office of Science Distinguished Scientist Fellow Award, for her pioneering approaches in climate modeling, discovering of unexpected impacts of regional climate change, and understanding extreme weather events and the future changes. Ruby.
I thank you very much, Deb, for introducing me, and thank you for having me here. I'm so excited to be participating in this panel to discuss with you the use of AI in climate and sustainability. So as the title of my presentation indicates, as you can see, AI and Earth system modeling. So my key point is that it is not either AI or Earth system modeling. Our efforts really emphasize the combined use of AI and AI and Earth system modeling to provide us actionable information about climate. So let me start by, first of all, introducing a little bit the problems that we are trying to solve, right? So you can see in this slide, it shows like last year, 2023, there are many billion-dollar weather and climate disasters in the United States. So you can see these from these symbols. Most of these disasters are related to thunderstorms, different kinds of thunderstorms that may be producing flooding, that can produce wind damages, hail damages, etc. But of course, we are also seeing increasing wildfires and heat waves around the world, as well as even in Washington state. So if we look back 40 years ago, around in the 1980s, if we look at billion-dollar disaster, weather and climate disaster, adjusted for inflation, such a billion-dollar extreme event happened on average like every 4 months. But now, looking at the same thing, we will be seeing one such event every 3 weeks. So you can see how quickly we have been really moving to a different climate where extreme events are happening more and more frequently. So this is why the National Climate Assessment Report that was published last year, they noted that our country is built for a climate that no longer exists. So in order to help us with climate policy as well as planning for adaptation, we really need to better understand and predict extreme events as well as how they may be changing in the future. So I would argue that Earth system models are foundational to provide us with predictions and projections for the future. Earth system models, they really encode our physical understanding of the climate system itself. For example, it represents processes related to the dynamics, like the atmospheric circulation and the ocean circulation, but it also represents a lot of the very complex physical processes in the climate systems, like clouds, turbulence, radiation, etc. So essentially, our challenge to model the Earth system is inherently a multi-scale challenge, because you can see really a wide range of scales involved in all these different processes. At the larger scale, like tens of thousands of kilometers, we need to resolve planetary waves. But if you go down all the way to the finer scale, we also need to resolve individual cumulus clouds, as well as even looking at what's happening inside the clouds, such as the cloud water droplet, etc. So it's really a wide range of scales that we are talking about. So generally, the typical Earth system models will be having a resolution of roughly 100 kilometers. So at that kind of resolution, we are able to resolve synoptic scale storms as well as planetary waves, but we are not able to resolve all the processes down at the lower scale. And therefore, there are lots of limitations in this type of Earth system models in simulating or predicting extreme events. But at the same time, now we do have global model that can actually resolve a lot of the cloud processes. So we call them cloud resolving models or kilometer scale models. So these models can resolve cumulus clouds, etc. And they are really good in simulating extreme events, and I will show you some examples there. But unfortunately, these models are really computationally very expensive. And our goal for simulating climate is not just to simulate a particular storm, but we need to simulate the climate statistics, which means you have to run your model over a long time period in order to know how the statistics may be changing in the future. So we have a lot of challenges now, right, at the two different scales. And so main question that I'm going to address in this presentation is how can AI enhance Earth system modeling for providing actionable climate information, particularly related to extreme events that I've been talking about. So I will give you some examples. In fact, with limited time, I will only give you 3 different examples. So the first example, we look at quasar scale models that I talk about of the resolution roughly like 100 kilometers that can only resolve planetary waves and synoptic storms. So here we know that these models cannot perform really well in simulating extreme events. So the question becomes, can we use AI to help us correct for the model errors or the biases in these models so that we can better simulate extreme events? So here we develop a convolutional neural network trained using data from climate models, where the climate models will run to mimic the observation, constantly being nudged towards the observation. So using these data to train the model, then we are able to correct for the biases in simulating storms, such as hurricanes, such as extratropical cyclones, but of course we are interested in atmospheric rivers. And the reason is obvious here, because in Washington State, most of our flooding events are related to atmospheric rivers. So here in this figure, I'm showing you on the left-hand side the observed frequency for atmospheric rivers. So there are a lot of them over the ocean, and when they make landfall, they produce heavy precipitation and flooding. In the middle, you can see the model biases when we run our model at roughly 100 kilometer resolution. So a lot of over-prediction of the frequency for atmospheric rivers at that kind of scale. And on the right-hand side, when we apply this AI bias correction scheme, we are able to much better simulate the frequency for atmospheric rivers, reducing the model biases by a lot. And so, as I said, this is not only for atmospheric rivers, it also works for many other types of storms that we worry about. And in my second example, here I'm talking about like going to the other scale, where we have global cloud resolving model run at roughly 3 kilometer resolution. So this is a model developed by the US Department of Energy. We call it the SCREAM model. And you are seeing an animation of from the model outputs of these simulations. And you can see at this kind of scale, the model is able to capture the clouds, the thunderstorms, etc. really realistically. You can see extratropical cyclones, atmospheric rivers, etc. But as I said, the problem is that these models are really computationally expensive. And in order to project climate change, we cannot just run it for a day or a few days. We have to run it for years, like hundreds of years, in order to look at the past as well as predict the future. So in our group, for our Department of Energy's project for the SCREAM model, recently, last year, we were able to successfully port our model to run on GPU computers. So a very important metric that we use to measure the computational efficiency of our models is what we call throughput. If you run your model on a very big computer for one day, how many years of simulation can you get? So we call it simulated year per day, or SYPD. So when we run our model on the biggest computer or the fastest computer in the world, which is called Frontier, is an exascale computer. And now we are able to break the record of actually simulating a little more than 1 year if we run our model for one day on this big computer. So for that, we were happy that we won the Gordon Bell Prize, Climate Prize last year for this breakthrough. But again, we're talking about running on a really big computer, right? So, and 1 year is not enough. We have to run it for many, many years. And in order to really produce good climate, we often have to tune our model or calibrate our model, because our models have a lot of representation of physical processes like clouds and turbulence and things like that, in order to produce a realistic depiction of the energy and the water cycles, we need to systematically tune our model parameters. And this itself is a very tedious task as well as a very computationally expensive task. So recently we were able to run 300 short simulations using this SCREAM model by perturbing the parameter values within our model. And then we use the data to train an emulator to emulate how sensitive our model simulations are to these various parameters of our model. So we were able to successfully create a surrogate model for this. And with that, we are now able to come up with optimized values for our model parameters so that we can reduce the model errors in simulating important quantities such as clouds and the radiation, etc. So you can see a big difference between the model error when we use the default value for the model parameters versus using the optimized values when the AI surrogate model help us to find these parameter values. So these are examples, one for low resolution and one for very high resolution. Now lastly, I want to just give you one more example where we've been looking at wildfires. Right? So we know that wildfires have been increasing quite a lot over the United States. And it has been difficult actually to represent wildfires in Earth system models because wildfires are controlled by many processes and factors, not only natural processes such as how moist the atmosphere is, how moist the soil is, etc., but it's also affected by human activities like the population, etc. So in order to represent that, we now develop a neural network model for wildfires, particularly capturing the emissions or the smokes coming from the wildfires that are causing problems for visibilities, for health, etc. So using this model, combined with climate model projection for the future, how the weather, the climate will be changing, as well as the projection for the socioeconomics, the changes in the population, etc., we are now able to project how wildfire emissions or the smokes will be changing in the future. So I particularly want to call your attention to the red dots over there. That's for the western forested region. And what I'm showing is the ratio for the future versus the present day. So if we compare the mid-century compared to early part of this century, then we can see for the western forested region, the models project an increase of the emission from 60 to 180%. And most of these increases occur over the summertime as well as the fall season. And using this kind of AI model, we can also try to identify what are the factors causing the changes that we are seeing. And so we identify that it is the changes in the soil moisture. So in the future, the soil will be drier, the temperature will be warmer, but also because of the warmer temperature, we will be getting more vegetation. So the increase in the vegetation will actually further increase this emission of wildfires by 50%. So the fuel coming from the vegetation is really important. So lastly, I just want to summarize a little bit what I talked about. So our efforts really focus on combining AI with Earth system model. And we think that AI can help us in many different ways. It can increase computational efficiency. It can improve model accuracy. It can help us quantify uncertainty, etc. And our ultimate goal is to really develop an Earth system model combining with AI that can help us develop a digital twin of the Earth. We can call it the digital Earth that can then help us use it for scientific discovery as well as providing actionable projections and predictions for the future. So with that, I thank you very much for your attention.
Thank you, Ruby. Great job. Next, I'd like to introduce Dr. Dale Durran. He's a professor of atmospheric sciences and an adjunct professor of applied mathematics at the University of Washington. Dale's research encompasses diverse areas in atmospheric sciences such as predictability, subseasonal forecasting, using machine learning, mountain meteorology, atmospheric waves, and numerical methods for simulating atmospheric flows. Most recently, he's been investigating the transformative potential of deep learning on numerical weather predictions. Dale is a fellow of the American Meteorological Society and has teamed up in 2019 with a grad student and a researcher at Microsoft to build the first model to demonstrate deep learning's potential in predicting the weather. Dale.
Thanks very much. So this is work that's been done with many people at the University of Washington. I actually am also 25% at Nvidia, but this is all University of Washington work, and I'm not speaking on Nvidia's part. But in any case, Nathaniel Creswell Clay, Andy Liu, Bowen Liu, and Raul Moreno are all grad students, and they're all at UW right now. And Matthias was a grad student, Matthias Karlbauer. He's back at the University of Tübingen. Okay, so I'd like us to start with a question, which is how complex should a deep learning Earth system model be? We've already heard a little bit about complexity. In some sense, this is a fairly well-answered question for large language models and computer vision. We'll get back to that. But, it's coming out a little small. But in any case, so to answer this question in the atmospheric context, let's ask ourselves, how many predictable degrees of freedom does the atmosphere have? Okay, so this is to say, what is there out there we need to forecast that is actually forecastable? And this depends on the time scale over which you want to forecast. If we have a short lead time forecast of an hour, well, it matters whether you have a thunderstorm over Pullman or over Moscow, Idaho, right? So there's a lot of predictable degrees of freedom on the fine scale, but if you want to go out to seasonal and subseasonal or even interannual scales, the degrees of freedom that are predictable drop drastically. Okay, so how do we predict these degrees of freedom with AI? The story is we can do this for completely different reasons than how we develop and define numerical weather prediction models. If it's a numerical weather prediction model, we need to worry about things like convergence, accuracy, and as Ruby just pointed out, we can hardly ever get a fine enough resolution in our model. There's always something that's falling off the end of our model, and we have a lot of work to do. But the story is potentially different when there are in fact only a few degrees of freedom that are predictable in the first place. So what I have up here, and I don't know if I can really, what we have here is a brief review of some of the leading weather forecast models, starting, however, with a numerical weather prediction model, the ECMWF so-called European model you sometimes hear people talk about, and it's got 911 spherical shells of data, which I mean is a variable that's defined around the globe on a single level. So there's 911 of those in the NWP model. That's the best model in the world. There's a series of models here in black that have somewhere ranging from 227 down to about 70 shells of data. I'm going to talk to you about a much more economical, parsimonious model. It's got 9 spherical shells of data. And the ocean, we're going to couple to an ocean model. Our ocean model is particularly basic, forecasting only sea surface temperature, so that's 1 spherical shell of data. The trainable parameters in our model are microscopic compared to a large language model, 3.5 million trainable parameters for the atmospheric model. There's a paper that just came out 4 days ago where they're bragging that they have a model with 3.5 million. We're going to use billion. So we're going to use a factor 1,000 less, 3.5 million in our model. And also, just as a point of reference, if we think about, we're going to be interested in climate models. If we think about the NCAR community climate model, it's got a bunch of different systems that hook together. It's got 25 levels in the soil model, in the land model itself. Okay, so these climate models are very, very complex. We're going to try to take a much more simplistic approach and see what we can do. Okay, so we're going to actually represent the model on a fairly novel grid that's familiar to astronomers. Any astronomers here? So, maybe not, or maybe I'm not looking carefully enough, but this is called the Helopix mesh. It hasn't hardly been used in atmospheric science. It's a wonderful mesh. It's a uniform mesh. We're going to be at 110 degree grid spacing, which is like a degree of latitude at the equator. We're going to train it on ERA 5, which is a reanalysis data set that all these weather models have used. But we're going to add a wrinkle. We're going to add satellite observations of clouds, so-called outgoing long-wave radiation. So this is going to get trained on real data as well as so-called reanalysis data. The loss function will be root mean square error over 1 day. I'll come back to that in a moment. We're going to use convolutional neural nets. We don't need to worry about that much, but here's a diamond-shaped stencil. The variables we're going to deal with, these 9 variables, are physically motivated choices. We didn't do a rigorous ablation study in terms of what variables work best. But we're going to send 3 variables down to the ocean in our coupled model. Something that's like surface pressure, surface wind speed, and this cloud cover called outgoing long-wave radiation. The ocean has only got sea surface temperature as its prognostic variable. That's going back to the atmosphere. And we're going to have prescribed fields like a land-sea fraction, the terrain elevation, and incoming solar radiation at the top of the atmosphere. But we don't give it latitude or longitude, so it doesn't learn explicitly that, for example, we're at the latitude and longitude coordinates of Seattle. Okay, and that's covered in the paper. Okay, so here's a quick animation just to show you what many of you may know, but if you're not in geophysics, the story being illustrated here is the atmosphere evolves much more rapidly than the ocean. This actually is a loop here. If you watch, it's moving to, these are the sea surface temperatures. This is a month-long loop. But we see the atmosphere proceeds at a much more rapid pace than the ocean sea surface temperatures change. Also, for future reference, this field that's color contoured is the 500 hectopascal height. It's sort of a contour map of the middle level of the mass of the atmosphere. Okay, so since there is these 2 differences in time scale, we couple the model. We build our model in 2 parts, an atmospheric model, an ocean model, and we couple it together just like they do in the Earth system models on asynchronous time scales. And then we'll take a look at what we get when we try to use this model to roll out the current climate. Okay, so what we've got here is a 1,000-year rollout of this model. That's 730,000 steps. And this is a type of model that's believed by many, erroneously, to smooth as it goes out in time or to become unstable. But obviously it didn't do that. Instead, it remained stable and actually is doing a very good job of computing the current climate. So I think in the interest of time, I won't go into details about what's plotted here, but this is year on the bottom axis, so there's time. There's 5 years on the bottom axis here. This is the average, that 500 hectopascal height around a latitude circle. And what you see is that the heights are high in the tropics, lower in the poles, and there's a seasonal cycle. And the little fine timescale variations here represent weather patterns that are simulated in the model or observed in the data. And you see these 2 plots look very similar. They're not perfectly the same because there's no event-to-event predictability on a 5-year time scale, but we're capturing the same kind of climate, and we've got it 1,000 years in the future as well. This upper right panel looks like the lower left. We've got the same kind of climate 1,000 years in the future. Also plotted here are the trends. There's no drift in this model. It's 2 orders of magnitude less than the drift in the IPCC CMIP6 models. And those are the models that were the basis for the last big IPCC report. Okay, so here again is just a quick look at a storm 100 years into the future or in the data, and this is also this 500 hectopascal height. The point is they look similar, and we have wind speed plotted here. We're not losing intensity. We're not losing detail. So what we like to know about how well this model performs? Well, there are measures of variability that are of interest, and we'll just pick one easy one to appreciate, which is spontaneous generation of typhoons, tropical cyclones in the western North Pacific. So what we have here is 30 years of reanalysis data, and the correct climatologies in the upper left here, and the strength of the storms are given by these different ranks here, with the red being the highest intensity storms. And then we have what our model spontaneously generates in the last 30 years of that 100-year forecast. And you can see that it's not doing a particularly bad, it's doing a pretty good job of matching the data. The storms are occurring a little too early, but let's compare it to the CMIP6 models that were used in the IPCC report. These models are run at the same resolution as our model, and this is what they do over here. Here's the NCAR Community Climate Model. Some of you may have heard of that. There's a Max Planck Institute model and so on. And the NCAR model is doing fairly good job, although it has some stuff out of season. The other 3 are having a lot more trouble. This very simple model, when you roll it out, generates spontaneously tropical cyclones in a way that is at least as good as the very expensive. We just heard from Ruby how expensive these models can be to run, though the CMIP6 models were cheaper than her model. But we're doing this with a much more economical machine learning model. Okay, So let's move on as we're getting close to the end here to talk about how we might use a model like this. For the it just does the current climate right now. It doesn't have anthropogenic forcing in it. We could try to use it for seasonal forecasts. In fact, we're going to go to a spot that could be particularly easy to forecast for, which is India, because we know there's a climatological monsoon in India that's of tremendous importance, monsoon onset. And so this is a forecast started on January 1st, 2017 for the onset in 2017. We have the average precipitation from ERA 5, this reanalysis data set, plotted in blue here for the first 2 weeks of June and then the second 2 weeks of June. And this is what the model forecasts. And it's not bad. These are 2-week averages. And this is 6 months into the future. Okay, so this is a fairly reasonable, in fact, it's actually quite reasonable, 6-month forecast of precipitation that is partly driven by the climatology, but still it's important to get the timing right, and it did a pretty good job on that. So that's a 6-month forecast of monsoon onset. So I want to wrap up then looping back to some of the stuff that we sort of heard about before, which is where does this type of modeling fit in the larger AI world? We have questions that can, be answered easily now with computer vision. You know, do we have here a cat or a dog? Forecasting the weather. How different are these problems? And we know the story is that at least at present, for computer vision and large language models, the bigger the model, the more data you give it, the better off you are. But that's not what we've seen here. This model is behaving differently, or it's behaving quite well as a very small economical model, and it's very likely due to the fact that we have governing equations that are driving one pattern to the next to the next. So it's not as arbitrary as language especially can be, right? So this gives us potential economies that we hopefully can exploit. So in summary, coupling the ocean and the atmosphere together gave us a very good model that runs for 1,000 years at least, reproducing the current climate and climate variability. And there's a bunch of stuff up here. There are other measures of variability on the large scale over a period of several months, and the model does quite good on these measures. I won't really go into all of the details here. It's a very efficient model. The 1,000-year simulation takes 12 hours on a single GPU, whereas the same simulation run on the NCAR CESM2 would take 90 days. So this is a small carbon footprint model, if you like, including for training. I think I might have the training up here. It trains on 4 GPUs in 3.5 days. These are relatively high-performance GPUs, but nevertheless, this is the kind of model you can develop at the university level. Okay, and in keeping with the idea that the WSAS is a really cutting-edge organization, the story is that we have a preprint about this model that just came out today on arXiv. So it was posted just today, and there's the reference to that.
That is what you call timely. Thank you, Dale. So our last speaker is Dr. Ben Richards. He's a marine ecologist at the National Oceanic and Atmospheric Administration. With a PhD in zoology from the University of Hawaii, Ben is specialized in the habitat preferences of large-bodied reef fish. Since joining NOAA in 1998, he has contributed to modeling the distribution of Pacific reef fish abundance and biomass associated with various natural and anthropogenic environmental factors. Transitioning sampling technologies to the use of optical camera systems, he's developed automated classification algorithms to support the analysis of the extreme amounts of data being collected. The current focus of Ben's research is on the distribution of marine resources along gradients of natural and anthropogenic factors, leveraging advanced automated analytical tools to enhance the assessments of ecosystem-based management. Ben is a recognized leader in the field of AI in marine sciences and has been awarded both the gold and bronze medals for scientific and technical achievement from the U.S. Department of Commerce and the NOAA Fisheries Silver Award. Looking forward to hearing what you're going to say, Ben.
Great, thank you all. It's a pleasure to be here. As Deb said, I'm representing NOAA. We have had a number of distinguished speakers already this morning talk primarily on the atmospheric side of things, which of course NOAA has a huge exposure to. I'm going to be talking primarily about the ocean systems. I am here representing also my colleagues Monica Youngman and Rob Redman. Monica and I co-chair NOAA's Executive Committee on Artificial Intelligence, which provides oversight and guidance to the new NOAA Center for Artificial Intelligence, directed by Rob Redman. Okay, much of NOAA's work in the sphere of artificial intelligence is governed and was initiated by the National AI Initiative Act of 2020, which set up the NOAA's Artificial Intelligence Strategy, which has 5 main goals you'll see here, and also established the NOAA Center for Artificial Intelligence as an aggregator and a single resource to democratize artificial intelligence across NOAA. So how is NOAA using artificial intelligence? As you've heard in many of the talks this morning, artificial intelligence is infusing almost every aspect of the research community. So NOAA's artificial intelligence portfolio spans everything from space weather, numerical weather prediction, operating uncrewed systems and adaptive sampling techniques throughout the ocean system, reviewing aerial and underwater imagery for specific targets of interest, and using both optical and acoustic technologies and signal processing within those technologies for studying protected resources, including cetaceans. So, what does that translate to? As you heard Marcia this morning mention that prior to her talk today, she queried the NAS community about the number of AI-related projects and came up with 60+ projects that were currently in the works. We did something similar, and not to brag, but we came up with over 260 funded projects directly related to artificial intelligence in the Earth-ocean system. As many of you know, NOAA is subdivided into 6 line offices: the National Ocean Service, Ocean and Atmospheric Research, the National Weather Service, National Marine Fisheries Service, and NESDIS. This histogram here shows the number of funded projects across various different AI domains, subdivided by the line offices. And as you see, primarily we're looking at image processing, hazard and extreme event prediction, weather and climate, and numeric modeling. So, with only 10 minutes to go through everything that NOAA is doing in the field of AI, I'm choosing just a few examples that illustrate primarily some of the ocean-related and fisheries-related work that we're doing with specific application to Washington State. And the first that I'll highlight here is work from a colleague of mine, Greg Dusick, at the National Ocean Service, looking at using convolutional neural networks paired with optical technologies for automated detection of rip currents. So rip currents are one of the main hazards for beachgoers in Washington State along the US seaboard. And human lifeguards are fairly good at detecting rip currents, putting up warning signs, but we don't have lifeguards at every beach throughout the US. What we are starting to do is have machine vision cameras that are coupled to the internet at many beach sites around the US that can automatically detect and put up warnings for rip currents that are seen in that particular location and time. So we also find that a lot of these new convolutional neural networks also conveniently have higher accuracy than human observers in detecting rip currents from optical imagery. Next is, of course, harmful algal blooms. As we see sea surface temperatures change, as we have increased nutrient runoff into nearshore waters, we're seeing harmful algal blooms, especially in Washington State, expanding both spatially and temporally, becoming more severe and more costly to shellfish industries, causing more frequent shellfish shutdowns. So we're using deep learning, convolutional neural networks again, for high-resolution forecasting of shellfish toxin levels. We have models that are trained on chemical footprints and also imagery that right now are having greater than 95% accuracy in predicting closure-level toxic events. So that can give industry a little bit more time to prepare for some of these events. Moving into the crowdsourcing side of things as well, we also have colleagues at the Ocean Service who have developed a tool called HabScope with NCOS and its partners. And this allows volunteers with minimal training to use a small piece of technology to provide real-time cell counts using a portable device, and then using TensorFlow and image recognition to classify cells from their image types. Switching over to the fisheries side of things, this is work from a colleague of mine, Cressmer Williams, at the Alaska Fisheries Science Center here. Traditional fisheries sampling, fisheries surveys, which we use for abundance indices that go into stock assessment modeling, which is used for fisheries management in the United States, in many areas involve trawl sampling. So we basically drag a net through the water, collect a bunch of fish, count them, measure them, figure out how old they are, and then they're removed from the population. Increasingly, NOAA Fisheries is moving away from extractive sampling into non-extractive sampling. So this is a project called CamTrawl, where they're using traditional trawl nets, dragged through the water, but to aggregate fish in front of a horizontally facing stereo camera system that images the fish, identifies them as a species, automatically sizes them, and then the cod end of the net is open, allowing the fish to pass out back into the environment relatively unharmed. And so what you see here in these plots here, in the green, this is a training set and a test case where the cod end was closed, so we were both imaging the fish and collecting them. The green is the human measurement, so the human size frequency distribution. So on the x-axis here, you have the size of the fish, the length of the fish in centimeters. On the y-axis here, you have proportionality. So the green here is what the humans came up with, actually measuring the fish on a measuring board. And then the red line here is what the cameras and the automated sizing algorithms came up with. And you can see right now a pretty good match between the two, which is quite encouraging. Also, not just fishery independent sampling, but also electronic monitoring. As most of you know, many commercial fishing vessels throughout US waters have observers on board that are monitoring the catch. Increasingly, it's harder to put human observers on commercial fishing vessels. It's costly, it's not necessarily the safest endeavor. And so we're moving towards replacing a lot of the human observers with optical camera technologies that can detect both targets of interest and bycatch as they come over the side of commercial fishing vessels for basically using machine learning to also sort the wheat from the chaff. Many of the images that are collected by the cameras don't have targets of interest. So instead of having a human have to look at every single image, we can have computer vision algorithms that automatically take away images that that have a low likelihood of having targets of interest in them. So with this, we can both increase our observer coverage, decrease the processing time for helping to monitor commercial fisheries. So now moving on to some of the challenges. As we all know, the accuracy, validity of a lot of these machine learning algorithms are predicated on a high amount of representative training data. And what we see in a lot of the marine sciences, of course, is right now the lack of a centralized database or a centralized repository of AI-ready training data. So this was a call that we put out to all of the PIs that were currently engaged in AI-related research throughout NOAA of what were their main challenges to kind of moving the ball forward. And what came up first was the access to labeled data. And in partnership with industry and academia, we need a centralized repository of AI-ready data that is accessible freely to researchers both within NOAA, private industry, academia, to all be working together off of the same data sets to catalyze research and development. So we have a proposal right now through the AI Executive Committee to start catalyzing development of that resource as we move forward. Okay, so that was a very, very quick overview of some of the work being done in NOAA. I would encourage you to investigate the other 257 projects that I didn't talk about today. And in order that I talked about the NOAA AI Center. So the NOAA AI Center has been set up as a one-stop repository and a broker for researchers both within NOAA, private industry, and academia to get together. Here is the website where you can investigate more. We have a variety of information on AI-ready data checklists for making your data AI-ready and working with NOAA and NOAA data. Thank you very much.
Thank you, Ben. Is this on? Okay. You can either thank me or be upset with me that I asked Ben to take out his 257 and narrow it down to maybe 5. But thanks, Ben. That was a great talk. So we've got a few questions for the panel here first, and then be thinking about what questions you might have. We'll have about 15 minutes for Q&A from all of you. This first question is going to be for Ruby and Ben. Can you share examples where AI has bridged the gap between different scientific domains? Ruby, you want to go first?
Yes, certainly, yeah. So I think AI is particularly useful when we are trying to look at something that actually don't have a set of equations yet. And particularly nowadays, when we look at Earth system models, we are no longer only simulating the natural processes because we wanted to know how the human systems, together with the natural processes, will be interacting with one another, and therefore define the future in terms of decarbonization scenarios, et cetera, et cetera. So I think AI is really useful in bridging the gap between what we know about the human systems, such as urban centers, processes that we don't actually have a good equation for, such as like I talk about the wildfires, where population and other human factors are also very important. So I think this is one example. And I wanted to also mention perhaps another example. I was really impressed yesterday by a talk that I attended. Well, it's really looking at partial differential equations. So essentially, PDE is the language of the nature. And so now we can use AI to really learn about the PDE. It can be hyperbolic, it can be elliptic, etc. And so because PDEs really apply to many different fields, right, in atmospheric science, in hydrology, in materials, etc. So I think really learning such operators of the PDE could bridge the gap between many different fields.
Thanks, Ruby. So Ben, can you share examples where AI has bridged the gap between different scientific domains?
Yeah, thanks. I think the first example that comes to mind is kind of a type of transfer learning. So some of the models that you saw in the talk that I gave primarily around object detection within optical imagery, a lot of the foundational object detection models don't really care what object they're looking at. It's how you tune them and how you train them. So Viame, which is an open source object detection toolkit that we developed largely in partnership with DARPA and IARPA. So a lot of the funding for that project came out of DARPA and IARPA, also with NOAA funding, but to develop object detection routines in an open source software framework that can be used across a variety of domains.
Thanks, Ben. So this next question is for all three of you. Dale, maybe you can kick off with it. What are the most promising areas of research within AI and climate modeling that need more attention?
Well, I certainly think that coupling to other aspects of the Earth system is very important. We're going to be putting a land model in our model, and that introduces applications in agriculture and in hydrology. I'm very eager to use satellite products like Normalized Differential Vegetation Index, which I think will tell a lot about vegetation health, which would be of direct interest to users, presumably, as well as helpful in forecasting the atmosphere. And I think there's a lot of opportunity to build in outputs that are of more direct interest to end users who don't care quite as much about the atmosphere.
Ben?
Yeah, I think similar to what Dale was saying, I think that the coupling between atmospheric and ocean models, and especially deep ocean models, is going to be critical. And one of the challenges is if you look at the density of empirical data that we get from surface weather stations compared to the density of empirical data that we get from deep ocean sensors is vastly different.
Yeah, so I also picked the coupling as one of the really important area that we need to pay attention to. I'm really impressed by what they show in their simulation that is stable over such a long time period and is so fast. But first of all, you need to have the sea surface temperature in order to drive the simulation. And where do the sea surface temperature comes from? It comes from a couple simulation where you have to represent both the atmosphere and the ocean and the sea ice and all of these together. So far, I think we haven't made enough progress in looking at the whole couple system, but I think this is an important area. Another one I want to maybe very briefly mention, which perhaps in some of the later questions we would encounter that as well, is to look at the generalizability of the AI model, right? So how well can they be generalized to really look at the future when the model, the AI models are built mainly upon data that is generated based on the observation or based on simulations from climate models for the present day. So.
Ruby, maybe you can talk a little bit more about that. How are these AI models then integrated with traditional climate models?
Yeah, so there are so many ways that AI can be integrated with Earth system models. So I show only maybe like 2 examples. One is to help us to better calibrate the model parameters. And I also talk about how we can bias correct climate models, especially those coarse resolution models where they can simulate really well some of the phenomena. But they also talk about downscaling or connecting to other models. I think this is really important because for what we call actionable climate information, the society really need to know not just like the average temperature over Washington state, for example. They need to know really the regional or the geographic specificity. And so I think downscaling, using the climate model and AI to downscale would be also very useful. Yeah.
Dale, do you want to add to that?
Well, I certainly agree that downscaling is one important thing. I do think something that will be interesting going forward is whether we can build a complete AI plus physics model that can forecast the response to anthropogenic forcing. And so this is going to require some physical constraints to the model. We didn't have any in our model. But I think the interesting thing about AI, once again, is you can ask, what is the constraint? The constraint is energy balance of the atmosphere. That is the constraint that's driven by the greenhouse gas forcing. And if we can get a hold of that into the AI model in a more holistic way than trying to do it sort of by getting every cloud simulated right and getting the reflectance off the top of the cloud right and so on, we have a shot at maybe building a much more efficient and yet more accurate tool.
Thanks. Ben, this one's for you. How can AI be used to enhance public understanding and engagement with climate science?
So I think there are a couple of aspects there. We heard some talk from Marcia this morning about education and outreach. And I think one of the things that we're going to see as we get some of these smaller, more parsimonious models that you can now run on a portable device in your pocket, allowing members of the public to engage in the search and in the scientific discovery of how different weather systems or ocean systems, climate change is going to affect the things that they particularly care about. And then also we talk a lot about large language models and generative AI now in terms of translating scientific literature into language that is more commonly consumable by the general public.
Thank you. I'm really excited for this last question. I'd like all 3 of you to answer it. How do you see AI for climate research evolving over the next 5 to 10 years? Go ahead.
Okay. To me, I think the generalizability and explainability are really 2 important aspects. So I talked about the generalizability before, right? So we really need to make sure that AI models are really generalizable so that it can be used out of sample. I think in the next 5 to 10 years, we have to make a lot of progress in that. But the second area is explainability. So far, we have focused quite a bit in our field in using AI to do prediction. But why can the AI be used to do prediction? So far as we can explain, I think there is always a problem of like how credible the predictions are. So we really need to be able to explain what is going on. So I think using AI for not only the prediction problem, but also for the discovery science, this is a little bit missing in our field. I think less done in our field than the prediction problem. So that would really help us to be able to better understand what is going on with the AI. But maybe one last point, AI really is usually really data hungry. So I think there is a possibility that because AI is so developing so quickly, right? So almost like every week you see a new paper in this, a new paper in that. So it is pushing us to really develop more data that can be used to feed the AI model. But the danger is that maybe the AI is moving so quickly that it outpaces the generation of high quality data, because it's not just data. We need high quality, well curated data. Yeah.
High quality, well curated, and labeled data. Dale?
Well, once again, Ruby's done a great job of hitting, I think, 3 high points here. Maybe I'll start with the last one and mention satellites, right? So where's our data source going to really come from? We have global coverage of satellites with increasingly novel or new products, particularly for end user products. I think these are going to be very important in hydrology, agriculture, maybe even get into public health here in terms of some end user products, which I believe will be a real emphasis in the AI connection into a model that's already AI. You can start to train it to make a product. If you have data to train on energy use in wind power, for example, you go directly into the wind power output from the AI model without all the other parameterizations based on nominal wind speeds and so on. So I think tighter connection to end users, novel satellite data products, and then I do want to get back to the explainability. I do agree that we haven't done a lot of that yet, but that's partly because no one really cares about explaining how a so-so model works. Once we have got models that we're really content with, that we think it matters, I think explainability will be a very interesting thing, and I believe that keeping the model parsimonious is helpful in that, and also that a key will be getting a hold of the latent space representations, keeping them a little more under control, and sampling what's happening in the latent space could be very helpful. So I think we will actually learn to use these models for scientific analysis in ways that 5 years from now we'll say, oh, this is how we should do it, and we don't quite know it all now.
I love what you just said, because I think as these climate change becomes more high consequence, explainability is going to become more and more important too. Thank you, Dale. Ben?
I think it's going to be hard to augment what Ruby and Dale have already said, and also Eric this morning talked a lot about what's going to be happening over the next 5 to 10 years. So the two things that interest me most is this tug of war right now between generalizable foundational models that can do everything no matter what you put into them, and these more parsimonious, bespoke, targeted models. And I think that the interplay between those two model types is going to be interesting over the next 5 to 10 years. And the trade-offs that we talked about a little bit between explainability and accuracy, and that tug of war that we're seeing right now between this model that we can explain absolutely everything that's going on at each step, but it's not very good, and this model that seems to be highly accurate, we don't know exactly what it's doing. And then finally, the last thing that really interests me is the hallucination effect, and when we have models that don't work. And I think over the next 5 to 10 years, we're going to be pushing up into a lot more of those situations where we find models that work in all of these areas, but not this one. And when we think about how models are developed and the training data that goes into the models, using models and using model failure to go back and look at biases and unconscious biases in training data and in research that has been done to date, and using it as a window into that.
Okay, this is your turn now. Are there questions out in the audience for this group of people? Please, Eric. Nope, she's coming.
It's a question for Dale, which is, how do we take the insights coming from the climate model over time and apply it to decision-making and insights about extreme weather events that we're facing, that some say are due to the changes in climate for decision-making and planning and so on?
Well, attribution due to climate change is already a difficult topic to begin with. There's some AI-assisted model that just came out that I haven't actually read up on. Theoretically, that might be helpful, but I would just like to back up a step and say I think that we will be able to take apart these forecasts, and I think they'll do fine on extreme weather. I don't think there's any real issue there. Our model does pretty well, actually, even at coarse resolution. So I think the goal will be to be able to do more targeted experiments more rapidly. It's a little bit like the rapid processing you mentioned, because these models run so fast. If the model does a good job of forecasting, we can do a lot more experiments with it, and with those extra experiments, hopefully pin down some of these things.
Thank you.
So I wanted to build off of Ben's last comment about model failures. And I'm curious how model failure helps us identify specific types of data that we need to be collecting going into the future, building on the things that, like Dale said, where satellites are now being used in different ways to collect new types of data. Are we using model failure to help us define new measurements that we should be making as we go forward to better train the AI systems?
Do I hit that one, Ben?
Dale's probably best to answer that one. I would say, from going back to kind of the early stages of some of the climate models, when some of the first climate models were starting to be developed, we realized that, just because of where weather stations are, a lot of the weather data was coming out of, highly populous regions in the United States and Europe, just because that's where the empirical data existed. And so realizing that, we need to both increase the amount of data and change the weighting on data that's coming out of highly populated versus rural population centers, things of that sort.
Maybe I can also add a little bit to this. So when we develop climate models, actually climate models have often been used to help us identify where observations are really needed. So we can run simulations and then we can identify, so there's a lot of sensitivity coming from, let's say, the Pacific Ocean or the Atlantic Ocean or things like that. So potentially, I think the AI models could also be used this way. But so far, I think that the diversity of the users of AI in our field is a little limited, as I said, mostly used for prediction, but not so much in helping us to identify where more measurements could be useful or other type of problems. Yeah.
If I can add one more thing to that. So another area that's very much on the leading edge right now is trying to do forecasts, starting with data directly to the forecast. So there is no gridded model in between. And if you have a model that actually is really good at that, then you can learn about what happens when you put extra data points in or not, right? So I think that's an interesting area. We're not sure how far that's going to go, but people are looking at that as well.
Thanks. Well, we have room for about one or, please, back here.
So first of all, thank you so much for the talks about AI in this field. I think it's very relevant, especially with the increasing amount of climate change. So in the morning from Eric's talk, actually, he was talking about the next inflection point in AI, which is multimodal AI and generative AI. And so all of you, I think, mentioned you're using visual models like CNNs and all those in your current work. Can you talk more about how this research can be augmented with these new types of models and how it can be improved?
So generative AI is definitely being used in this area. I don't work much with generative AI models, though a little bit. And when we look into the future, we often need to talk about distributions of possible outcomes. So this is the ensemble idea, a whole bunch of nominally likely outcomes. And generative AI is very good for this because you can start probabilistically directly generating a probabilistic forecast. So that's one thing generative AI is particularly good for. it's also potentially useful for these downscaling problems as well. So this is all being explored, even though we didn't quite get into it.
Either one of you guys? Yeah. Look over here.
Hi. Thank you for all this. I'm a natural resource manager. And for 30 years, I've watched species decline in Puget Sound. I've watched pollution increase. I've watched habitats be altered. I'm wondering, how can people like me who are on the front line of sustainability issues connect with folks, like you who are on the forefront of using AI to solve these types of problems?
So maybe one thing that could be helpful, I think, is also going back to the generative AI or large language model. Because actually, in our field, we generate so much data, right, coming from climate models and now also coming from AI models and things like that. And it's really difficult for stakeholders to digest the information. So one thing that has been really discussed is to use this kind of large language model to make it easy for stakeholders to access the information and digest the information. Like you can get all these model outputs into the system so that you can ask questions in your own way, and it would give you an answer that you can easily understand. So I think this could be one thing that might be helpful.
And I think if I understand the question correctly, we've talked about a lot of different research endeavors that are using artificial intelligence in one form or another. But where you come in on the management side is defining the important questions. What are the questions that we need to research, that we need to answer to have management level impact? And so certainly from the NOAA perspective, here in Seattle, you have the Northwest Fisheries Science Center, you have the Alaska Fisheries Science Center. So working with your state and local partners to define those management relevant questions to drive research.
Right over here.
Yeah, Noel and I work a lot with electric utilities, and we're seeing the impact of the wildfires in PG&E in California. The company, literally went bankrupt. We're seeing the Lahaina fire. What can we do to simulate those events, which to you all should be pretty obvious? What can we do to simulate those events ahead of time to truly get the attention of executives to kind of have some foresight and not actually have them in real time, please?
Yeah, so I think you're starting to see a lot of that already, and part of it is market driven, as you've mentioned, because of the bankruptcies of many of these utilities that have been found negligent in various areas. And so we're looking at fire weather predictability. We're looking at, when I say we, the scientific community in general and industry, looking at models and forecasting to automatically cut power to different areas if there is high fire weather danger, looking at being able to better model soil moisture content, vegetation, fuel load, to better and more accurately predict areas that are at higher risk of both ignition and spread. And then what mitigation factors can be put in place either a priori or in rapid response mode to reduce the risks of events like that.
We're also going to have some talks in the next session, I believe, on wildfires. So I think bringing that question back up to the foreground after that discussion could be valuable as well. Okay, with that, I'd like to say thank you to this group here, Ben, Dale, and Ruby. Thank you for your time.